Okay, let's look at part 2 of chapter 5. So we're going to be looking at systems, external and internal forces, and vector addition. Now, we don't need to know too much about the systems idea. Mostly it introduces a couple of words for us, and it introduces the idea of a system. So let's talk about that. What's a system? Well, we usually talk about a system of objects when a physicist is trying to explain something, and we just want to talk about a small group of objects that are interacting with each other. Okay, so we have to limit it. And so this box here that's drawn with a dashed line is showing the limits of the system. And this system consists of this orange sitting in this cart. Okay, so let's go look at the next picture. Okay, now the idea is that the orange was experiencing a force. And this is an external force. It comes from outside the system. So that is one of the words that, or phrases that you're supposed to figure out is external force. Comes from outside the system. And what happens is that the orange is going to be pulled by that force and it's going to accelerate. So external forces accelerate systems. And when people look at these arrows, again, they sometimes say, aren't those going to cancel? No, because this is the force of the apple on the orange. This is the force of the orange on the apple. And so the apple will still be able to go forward if he can find another force that's bigger in the other direction. So the apple pushes on the earth and the earth pushes on the apple. And that provides the apple with two forces. And so he digs in his feet, pushes hard, and he can pull the orange. Okay? Now, what would happen if we put them both inside our system, but we don't let them interact with the world? So the world is not part of this system now, which means the apple can't dig in with his feet. And so it's like it's a frictionless surface. So if you can imagine these two on a slippery, icy pond, well, the apple can't pull the orange anymore and to move himself at the same time. Now, he could turn around and yank on the rope, and then the orange would slide one way and the apple would slide the other way. And that would be allowed, okay? But in that case, the whole system doesn't accelerate. The orange would slide this way, the apple would slide this way, because that's the only force on the apple and the only force on the orange. And they would meet in the middle, and the system won't have actually moved. The middle or center of mass of the system would stay in the same place. Okay, so if you don't have a world to push on, the apple cannot get another force to counteract the force of the orange. Okay, so now we're going to allow the world back into the system. So now we've got a system, and now the external force is the force from the world. So the apple is pushing on the earth, and the earth is pushing back on the apple, and that force allows the apple to continue moving and pushing the orange along. So again, we need an external force to accelerate this system. Internal forces won't accelerate. We'll talk about that a little bit more in another one also, the next chapter. Okay, now the other thing in this section is vector addition. So remember we talked about vectors. Vectors have a magnitude and a direction. And so some of the things that we represent by a vector, as a vector, are the force, velocity, and acceleration. And so they can all be represented by an arrow. Now the thing is that in physics, sometimes we have things that go in more than one direction. And because of that, we have to use both x and y coordinates. So let's say here we have some vectors, and we've got two vectors, and let's call them A and B. And the idea is that I need to add them together to get a resultant vector. It might be like two forces, but two forces that are pushing on a box, not opposite to each other, but at 90 degrees to each other. Okay, think about two dogs pulling on a blanket or something, okay? But they're not opposite. They're working slightly together. They're at 90 degrees. Okay, so anyway, so here we've got these two vectors, and the way that you can add them up is what's called the parallelogram rule. The parallelogram rule is where you have the two vectors with their ends touching each other, okay? And so A and B. And what you do is what's called completing the parallelogram. So complete, oh boy. So complete the parallelogram. So that means you draw two parallel sides. So you would draw a side here and a side there. And then you would get a resultant. So here's our resultant vector, which goes from where they started, their ends, to their tips. Okay, so that's completing the parallelogram, and your resultant is that diagonal. And if you want to know how long that diagonal is, of course, you could use Pythagoras' theorem, right? A squared plus B squared equals C squared. Because these sides are now, we've got, well, A here and B here, and this could be C, the resultant. Okay, so these two were perpendicular to each other. However, to use the parallelogram rule, they don't have to be perpendicular to each other. So I'll show you that in a little while. You just have to complete a parallelogram. If they're not perpendicular, then you can't use Pythagoras' theorem. Okay, now another way to do it is what's called tip to tail, or tail to tip. And that's the one that a lot of physicists like. So you've got your two vectors, A and B. And why do physicists like it better? Because you can do it with many, many, many vectors, 3, 4, 5, 6. Whereas the parallelogram one is basically two at a time. So for this one, what you do is you take your tip of one vector and put it to the tail of the next one. So my B and my A. And then your resultant goes from the tail to the tip. Okay, so it looks the same, right? It should be the same. It's the same resultant. But it's just gotten a little bit different there. And the nice thing is that I could add another vector on if I wanted to. I could add a vector this way, and then another vector this way, and another vector like this. And my resultant will always be from the tail to the tip. So anyway, so this one's nice for physicists who have lots and lots of vectors because they're looking at lots of forces, for instance. And so this one is very popular for physicists. Okay, but that's called the tip to tail method. And usually you guys are just going to have two vectors. If you were in the real class, you would have three vectors to add up. But I haven't got the lab for you to do that. Okay, so anyway, as I was saying, if they're perpendicular, then you can use Pythagoras to find the hypotenuse, which is the resultant. And there are some special ones. You probably remember the 45-degree angle. When you put in 1 and 1, then the hypotenuse or resultant is square root of 2. So if A is 1 and B is 1, then C or R, the resultant, is square root of 2. Now, you can always do multiples of these too. So in other words, if I had the square root of 2 is 1.414. So what if I made this side 10 and this side 10? Well, then the hypotenuse would be 10 times greater. So instead of 1.414, it would be 14.14. And somewhere you've got a homework problem where one side is 100 and another side is 100. So what's the hypotenuse? 141.4. Okay, so anyway, so you can use multiples of it. And it doesn't have to be tens. It could be 2, 3, 6, whatever. Now, another triangle that physicists like to use because the numbers are so nice is what's called the 3, 4, 5 triangle. And so let's look at a triangle that's a 3, 4, 5 triangle. And so I'm going to erase, oops, I'm going to cancel out these for the moment. Okay, so instead of 30, 40, 50, let's just look at the basis of why 3 and 4 and 5 make this beautiful triangle. So let's look at the theory of Pythagoras, right? So a squared plus b squared equals c squared. And so a, let's make 3. B is 4. And 3 squared plus 4 squared is 9 plus 16, which makes 25, which is why, what is C going to be? C is going to be 5, right? 25 is C squared. So 3, 4, 5 triangles are beautiful things. And again, you can always have multiples of them. So it could be 30, 40, 50, or maybe it's 6, 8, 10, or maybe it's 4 times 3, that would be 12. 4 times 4 would be 16. 4 times 5 would be 20. Right? So you can have all these possibilities. So when you're doing your homework, keep your eye out for 3, 4, 5 triangles. Okay, now, like I said, to use the parallelogram rule, you don't have to have the vectors actually perpendicular to each other. You just have to be able to complete the parallelogram. So you've got some homework problems like this, where you'll have this, like this airplane. The engine is pushing one way, so this would be the force of the engine, or the speed of the plane in that direction. Okay, so let's make that velocity. And then you've got the wind velocity pushing in the other direction, in another direction. Okay, and so there's a resultant that's due to that. And so let's look at this part B here. Okay, so you would complete the parallelogram. So you would draw upwards and over to complete a parallelogram. And your resultant, of course, would be this, right? That would be your resultant. And this is called adding vectors graphically. We don't actually know what that value is mathematically yet. We can actually measure it on a piece of graph paper. So sometimes physicists do things graphically without knowing what the numbers are. But of course, most physicists would use trig in this case. Okay, but you could also do it graphically, where you could count the, use a ruler to measure the distance. Okay, on a piece of graph paper or something. Okay, and so you can see what happens is that you just have to complete the parallelogram. So if we complete the parallelogram of C, that's going to be down, over, right? And so where is our resultant? Always from where they start to where they end up. Now, here's an airplane that is trying to move at 80 kilometers per hour in the forward direction, but there's a wind of 60 kilometers per hour to the right here. Okay, so what's the resultant? How come they can say 100? Well, this is a 3, 4, 5 triangle, right? This one is 60, which would be 3 times 20. This is 80, which is 4 times 20. And so our final answer would be 5 times 20, or 100. So watch out for those sneaky 3, 4, 5 triangles. You'll see a couple of them in your homeworks and maybe on a test. Okay, and the same thing happens here. We've got a boat crossing water. So you can figure out, well, to actually get across the river straight across, you can't just point your boat straight because the river is going to carry you down, right? It's going to add together and your final velocity will look downwards. So which one of these boats has the best chance of going straight across the river? Well, and here's another 3, 4, 5 triangle, right? 3 down, 4 to the right, 5 will be your final velocity. Okay, now some other things that you're supposed to look at in this section is the idea that any vector can be broken into 2 perpendicular component vectors. So an x and a y component, you can think. And so we've got a vector v. We draw lines to indicate x and y. And then what we do is we draw parallel lines to the axes. So this is like going in reverse of the parallel addition rule. So we're basically completing the parallel. Let me grab the different color. Completing the parallel. And then what we're doing is saying that those values are our new vectors. So we have 2 vectors that we could have used to create this as the resultant, right? So those values are our x and our y components. And sometimes we'll talk about that when we're talking about, like, we're throwing a rock or a baseball and we throw it at an angle. So we can break that into 2 components. One of them is vertical, that would be the y component, and one of them is horizontal, the x component. And that will come in when we're talking about objects and falling through the air. Okay, so we'll do a chapter where we think about that. But we don't usually have to do the math on that. Again, that would require trig, and that's not this class. Okay. Now, here's a girl being held up by a rope, and we looked at this a little bit in homework the other day. The thing is that we asked which rope has more tension. And I said, well, you can sort of imagine that it's the one that's closest to being upright. But how can we really figure that out? Okay, so let's look at that and look at how to do it graphically. Okay, so the idea is that we draw a weight for the girl. So this is her weight downwards. And we know if she's in equilibrium, there is a equal force upwards. So the tension in the ropes are pulling her upwards, and those two have to be equal to each other. Okay, so what we do next is we figure out how much of that force is on each rope. So we draw lines that are parallel to the rope that meet at the tip of the arrow there. And the thing is that now we know the value along each of these ropes of the tension. And so now we can use the 2 arrows that we're going to get from that. Okay, tension in this one. And here, some more tension. Those are going to be the values of the tension. And which one is bigger? Well, the one from the rope that is more upright. Okay, so yeah, that rope is taking most of the tension. The one off to the side is taking less of the girl's weight. But together, they add up to her weight. So, same sort of thing. Here's a lantern. And it's being held by 2 ropes fairly close together. And the tension in the ropes, if you draw parallel lines, okay, then you end up with those blue arrows as being the contributors, T1 and T2. Okay, now, if we take that lantern and we put the same lantern with the same weight on some ropes that are spread way out. Okay, so here's our weight of the lantern, how much force or tension we need upwards that equals the weight. Then we have to draw parallel lines, and this is not easy. That's supposed to be parallel to this one. This is supposed to be parallel to the other one. And what you can see right away is we are getting much greater forces. These are much longer than on the previous page. And again, it's that idea that the ropes, that if they were more upright, the closer they are to being upright, two ropes, they would each hold half her weight. But when you start to spread it out like that, then what happens is they only go up a little, but they go out a large distance. So they have a big tension to hold a little bit of force in the upwards direction. And so because of that, the small force upwards versus a larger force to the side means that what you end up with is a much larger tension altogether. And so the rope is more likely to break because it has greater amounts of tension on it. So if you are sitting in a swing, each rope being parallel like that, they're each just holding half your weight, like Harry the Sign Painter. But what about if you're lying in a hammock? Well, now your weight has to be supported by these ropes that are spread at a great distance. And so what happens is that the tension is much greater. Okay, so you end up with much greater tension in the hammock. Okay, well, that's the end of this chapter. And let's see, there's usually a story I tell with this, the hammock story. Once upon a time, my mother was swinging in a hammock that we had tied underneath an apple tree, and the rope broke, and she fell, and her spine hit an apple. Now, you might think this is a sad story, but actually my mom had had a bad back, a slip disc, for years. When it hit the apple, it actually pushed the disc back into place. And she never had back trouble after that. So anyway, so the moral of the story is be careful. Hammocks can fall down because ropes are under great tension. But also sometimes accidents can be glad. Okay, all right. I'll see you next time with chapter 6.